Okay, everybody, welcome to AP Physics. Today we are studying two-dimensional motion. So the first thing that you have to, well, there's some key words that you need to consider. Two-dimensional. If this is brand new to you, the key words are independent, okay, and time. Okay, and this is kind of hard, okay, because when you grow up, you play catch, right, with your friends, and you throw a ball, and the ball flies through the air, and you catch it. And your brain is doing all this math calculations, like this brain is saying, okay, I'm going to need to throw it, so hard. And then this brain is saying, well, I need to catch it. I need to move to a specific spot where the ball is going to be. So your brain is really good at this kind of physics. And how did your brain learn that? Well, trial and error is really how it did it. Okay? So the confusing part of this two-dimensional motion is separating something that you've always seen as a combination. So as you've seen this ball fly through the air, there's one ball in one spot at one time, but there's a combination of things that happen with this ball, and they happen independently from each other, except for they have one thing that they do share, or two things. The first thing is the ball, the second thing is time, okay? So what we're talking about here then is the motion in the horizontal direction and the motion in the vertical direction. Okay, so these are the two things that are completely independent of each other when we do the math. We do the math with these two pieces independently. There are ways to do it together with graphing techniques, but that only goes so far. To really understand this, you have to get this independent motion understood. And why do you think we have time here spelled with a Y? Well, it's because most of the time, the occurrence is dictated by whatever is happening in the Y direction. Because if I threw a ball up, and there was no acceleration, do you know what the path would look like? Well, the path would be straight, right? Because Newton's first law is, things maintain their state of motion unless acted on by an outside net force. So that would go a straight line, but we know that doesn't happen. Okay? If I threw, let's just say that I make this a little simpler. If I threw a ball straight, would it go forever? No, it wouldn't go forever. How come? Because it doesn't go straight. It ends up getting pulled down towards the earth because of the force of gravity. So this whole velocity in the x direction only can occur for as much time that what's happening in the Y allows it to occur. Because eventually it's going to get pulled down to the earth, and then the ball is going to land and stop, right? So that's why we usually determine time with the Y characteristics. Now, the time when this doesn't work is if you are throwing a ball, like let's say you're throwing a ball here, and you hit a wall, and if you're not given like this displacement here, then you might end up finding time using the x part of the velocity. Okay, not very common to ask questions that way, and you'll probably get it or see it when they ask it. So when we look at this parabolic motion, so I'll just say that this is the path of the ball, okay? And in reality, though, there's air friction and things, right? So in reality, the path of the ball is going to be more like this. You know, depending on the speeds and how far you're throwing and stuff like that. But at this point, we're not factoring in any other forces besides gravity. So that is not what we're studying. We are studying what would happen if you were throwing a ball without, like on the moon. There's going to be no air up there, right? So on the moon, there will be no air friction. So we're kind of studying what happens to things on the moon. So if you look at this, initially, my velocity, now if this was a perfect parabola, might be a little bit easier to see. Still not perfect, but initially my velocity is going to be tangent, like an instantaneous velocity is tangent to the curve at any point of the curve. So in this case, this is my velocity. Okay, now if you start resolving this into vectors, you will see that it is made out of the x part and the y part. Okay? Now here's the thing, if there's no friction, then there's no force, and therefore there's no acceleration that happens in the x direction. So throughout the whole problem then, what does that mean? What does that mean? Yes, that means that this value here, whatever it is, will remain constant throughout the whole situation. So then what happens here is this part of the triangle is the same, no matter where you're at. Now, we know that balls don't tend to just keep going. At this point, our velocity would look like that, okay? Notice the x here, because the size of the arrow is telling you what the magnitude is. So this and this should both be the same value, because there's no acceleration in the x direction. Okay? But you can see here now we have, oops. You can see, oh boy. Picture may have adjusted there, but the x value is still the same throughout, but the y has changed. Why has that changed? Well, the velocity in the y direction, we could say was positive here, right? Because we kind of by convention we say up is positive. Which direction is, in this case, acceleration? It's negative, which means it's the exactly opposite direction of what I deem positive. So when you have those two different signs of the acceleration and the velocity, it's slowing down, right? So what happened is this acceleration is taking away from this velocity every instant in time, and at this point then we can signify that it's much smaller. Now this is on the test, so you're going to have to reproduce this on the test. What's our velocity right here at the top of the parabolic path? Well, it's all x. Should maybe did that in green. Okay, notice all of these x's should be the same length, signifying that there's no acceleration, there's no change in the x direction. Is there a y in this case? No, there's no y. And then when we get down to, another place over here, we'll see that that would be our velocity. We have our x velocity that is still the same. and then we have the y part. Now, in this case, the y is that negative or positive? It's negative direction because we deemed over here what we're going to call positive for the whole rest of the question. Which direction is my acceleration in this case? Negative, so we need to expect that the y is going to do what? Get bigger and bigger because they're in the same direction. And so then we get back down to here and we have our resultant or our actual velocity. But what we work with then is the x and the y. Okay, you can see that the y has gotten bigger. Now, if I would have drawn this parabolic path just right, if we remain on the same plane, which I guess I did go a little higher than that, you're going to have the exact same velocity magnitude. But the direction isn't opposite. And the reason why the direction isn't opposite is because our velocity has a piece that doesn't change and one piece that does change. Okay, so does that kind of explain how I expect you to start understanding the independence between the x and the y variable? Let's see if I can find a little demonstration here online to help with that. Okay, so this link here is a link that is of the famous Mythbusters YouTube video. And what they did on that link, and you'll be able to see it, is they took a gun and they fired a bullet out of it going very, very, very fast. And that was at a certain X plane. And then over here they figured out where it should land, and they had a camera here, and they had, you know, an electrical system that had another bullet that was dropped from the same height. And so they were able to catch on camera what happened. Now, you know, the whole electrical system could have been off too a little bit. That's another place. So what they found is, and we know this is a high velocity coming out of the gun, is that this bullet then ended up hitting, that wasn't a very good parabolic path, at the same time as this bullet did. So these two bullets hit, actually they said, well, you watch the video, it's like 39 milliseconds off, which is not very much. It's enough to say, hey, you know, we can see that this is actuality. And you know, this is something physicists have known for a long time, but now Mythbusters did a really good job of showing it. You've probably seen this in physical science with another way, but the other way is you drop two balls, or you shoot one ball off a ramp and drop the other. But that should be enough for you to believe that what we started out with, this independence idea. Independence. So, when you have a problem such as this cliff problem, and the car is driving off the cliff, okay, and let's just say that they give you a displacement here. So let's say it's 100 meters, okay, and you're trying to figure out, well, how far away from the cliff is this going to land? Well, this velocity in the x direction, let's just say it's 30 meters per second. Okay? Keeping in mind that that will be constant throughout the whole entire situation. So, if you figure out x down here is going to equal your velocity in the x direction times time. Do you agree with that? So we have our velocity in the x direction, because that's constant throughout the whole situation. It's the time that we have to figure out. Well, this height here is going to determine how far the car gets to drop in the y direction. So we can use that distance to figure out how much time it's going to take, because what do we always know about the y direction and acceleration? Acceleration, or little g, is always 10 downwards. Okay? So we're going to use that. So we're going to look at our formula and we're going to say, how do we find time? Okay. Well, V sub naught, displacement, time, acceleration. You need to have this checklist every time, or else I won't help you with your problems. And then you start filling it in. V, we don't know. V sub naught is 0 in the y direction. Do you agree? The x in the y direction is negative 100. Time we don't know. That's what we're looking for. Acceleration is negative 10 meters per second squared. Now it's easy to see that you could put both of these in positive. That's fine. But the displacement starts here, ends down here. It's in the downward direction. So whatever your acceleration is, as far as the sign, that you have to maintain that throughout the whole problem. Now here's the other thing you need to have before I help you. You need to have your formulas written on the top of the page. And the reason why that is because, well, one, it'll help you memorize it, and two, your brain starts seeing all this stuff and putting it together, and three, it's kind of like, what do you have this checklist for? Well, you have this checklist so you can see what variables you have to use, right? One more thing about this. You write a checklist for X stuff, you write a checklist for Y stuff, you never write a checklist for X, Y stuff. You never do math with X, Y stuff. You only do math with X stuff and Y stuff independently and put it all back together at the end. Okay, so in this case, I'm looking at this, and I like this formula because I have displacement, I have a V sub naught of 0, which cancels that out, I have acceleration, and I'm looking for time. So what I do is x equals 1/2 at squared, okay, because my V sub naught canceled out. T then equals the square root of 2x over little g. T then equals the square root of 2 times negative 100 all over negative 10. So time equals, so the square root of 20, Joel, or whoever, what is it? 4.47 seconds. So that's how much time it's going to take this car to fall. Once it hits the ground, it's going to stop going in the x direction. So that's when we can take this and plug it in there. So our displacement in the x direction becomes 30 meters per second times 4.47 seconds. Our displacement in the x direction is, what's the displacement? So the x displacement is 134.1 meters. Okay, so there's kind of an introduction to two-dimensional notes there for you. Hopefully that helps.